Hello, everyone. This talk is going to be about pretty much distributed systems and event sourcing, but from a slightly different angle. I would like to talk a little bit about how to design your systems so that they are a little bit more durable, they are more fault tolerant, and they have some really nice additional properties. But I want to start with something really terrifying, the monolith. If you've been working in any software company, and that's the case for me for the last 4 or 5 places where I work with, there was always some sort of a monolith, one gigantic pile of code. It wasn't even an application, it was just a big chunk of code that was doing everything. It was front end, it was back end, it was front office, back office, it was generating invoices, it was doing some reporting, pretty much everything. There was just one huge application deployed somewhere. And many people realize that it's really hard to maintain it, because once you modify something in the reporting module, suddenly something breaks in the front end, and vice versa. That's a really terrible thing to do. So all the people suddenly came up with an idea, not that suddenly, as we will see in a second, but many people came up with an idea that, you know what, we're going to take this monolith and we're going to split it into something different. We're going to split it into many smaller pieces. And this is what it's called, and I'm doing my best not to say this word, but I'm just going to do it once. This is what used to be called these days microservices. So just splitting one huge chunk of code into smaller services. This is not a new idea, actually. So this is Jeff Bezos in 2002, so 15 years ago. He said that all the components within all the Amazon infrastructure, he's a CEO of Amazon, all the components within the Amazon infrastructure are supposed to communicate with each other using interfaces, using some sort of protocols rather than just having like a shared network file systems or any other way to like share databases and so on and so forth. And this turned out to be a pretty good idea because Amazon still exists and it seems to be a pretty successful company. However, it wasn't that easy in the beginning. So the Amazon's architecture was looking something like this around 2000. Oh, sorry, this is like actually an Ebola virus. So the architecture in Amazon was even worse than that because it was looking something like this. There were hundreds, maybe thousands of different services communicating with each other. And even though it actually works, it was a nightmare to maintain. And they all learned this lesson already because it happened in 2009, actually. So there's an interesting memo that Steve Yege, a former employee of Amazon, and then he worked at Google. I think he still works there. He's a very influential guy, and he wrote this internal memo to all the Google employees because he was contrasting how Amazon was working, because he was working there for like 6 years, and then he was comparing this to how Google works and what Amazon is doing good and what Amazon is doing bad compared to Google. This was supposed to be an internal memo, but he just like misclicked something in the Google Plus platform, and by coincidence and by accident, he published it to the whole internet. That's why we can read this really interesting story. So that's what he said. He said, code base is a disaster with no engineering standards because there are so many services that it's so hard to grasp everything and to figure out what should actually be the standard across the whole code base because there are so many code bases. But that's just the beginning. He also said that pager escalation gets way harder. Now imagine if you have a single application and something fails in that application. That's okay. I mean, you have one huge stack trace, you can go through all the layers and everything is clear. When you have multiple services, what you get is you have an error in one service, but probably the root cause of this problem is 7 services later or earlier in well, there's not even a call stack. There's just a bunch of services calling each other. And if teams, because most likely there's going to be many teams, if teams are not mature enough, then they're just going to be bouncing the ball and pretending that this is not their fault, just trying to play a little bit and just get some time. So what used to be a problem that you could easily fix within 15 minutes and one deployment becomes basically a murder scene where you're trying to figure out who made the problem. But that's not it. So that's really an interesting problem, and not many people are thinking about it. Every single service in your ecosystem can become a potential source of denial of service attack on the rest of the system. You may make a programming mistake. You may deploy something in too many or too little instances, and suddenly one service takes down another service and another and another and another, and your whole ecosystem just breaks because one service was misbehaving. So suddenly every single service in your system has to protect itself from these kinds of attacks. And that's really weird, but that's kind of something they figure out. And one more thing. They really needed a way to locate services. So it's not that easy. When you have a monolith or when you have just a bunch of services, you can just hard code addresses in the configuration. But now you need a special service that just holds the addresses of all the other services. They are registering, deregistering, they have some heartbeats and so on and so forth. And this itself, first of all, becomes quite complex. Just read how Zookeeper works or Consul works. They are really quite complex pieces of software. They are also becoming bottlenecks. And when your service discovery goes down, even if all of your services are up, your system is not working because no one sees any other service. And that's just the beginning. And he also says, and this is like quite obvious, debugging becomes really, really, really hard. And basically, there's no other way to debug your system than just to go to production and see how it behaves, which is really weird. And that was yet another of his points. So after hearing all of this monolith doesn't seem so bad after all. Yet Amazon went this way, and it turned out that it wasn't that bad after all. I mean, once again, Amazon is a successful company. They are doing their web services, they are doing all of their platforms, and it's still all based on the services. So it wasn't that bad after all. And you know what? This memo that was written by Jeff Bezos at the very beginning, that every team is supposed to now communicate using protocols, the last point of that memo, I'm not even sure if it's true or it's just an urban legend. The last point of that memo is that if someone doesn't like this, he will be fired. That's it. But the people weren't afraid. They just figured out that services are actually the right way to go. They just need to somehow overcome all these issues. So how we can split the monolith? Let's just go a little bit practical. We kind of know what are the disadvantages because that's what I started with. And we would like to split our application. I'm saying Java, but the same principles apply for any other language. So the easiest way to do is to take your application and first logically tear it apart into packages or modules or whatever, and figure out what are the interfaces between these modules. Because these interfaces will later become boundaries of your system, boundaries of your bounded context, if you're familiar with domain-driven design. And this sounds really simple. So you have two classes, two subsystems in your whole monolith that used to communicate with each other using a standard Java interface. And now they will be communicating using a Java interface abstraction, but this abstraction is going to be transported over HTTP. So here we have it. This is a tiny little piece of Java code that any other language would do. It's really simple, but the point is, it's also very cheap and very fast. As a matter of fact, in JVM, when I create such a simple method, it's going to be inlined, which means that I'm not paying the cost of calling this method at all, most likely. So when I call this method, pretty much the code of that method, the body of that method, will be inlined into a place where it was invoked, so there is absolutely no cost of calling the method called triple. But now with the magic of annotations, and in this particular example I'm using Fagin, which is like a really brilliant library actually. You can just put a bunch of annotations on your Java interface, skip the implementation, and suddenly your Java interface become a RESTful interface. You see, I'm actually doing like calling this method is actually calling GET request on some sort of address. And that's brilliant. It actually works, and it seems like a very intuitive way of splitting your system. So it used to be a Java interface with virtually no cost, and now it's just calling a Java interface. So from the client perspective, it behaves the same way, or it almost behaves the same way. The problem is that calling an HTTP interface, calling a RESTful interface, is totally different than calling a Java interface. Now, every single line on this slide is a possible source of an error. And providing that we actually reach this stage, because many, many things can fail. You might not have network connection, or your network connection can be down. You might not have a connection to a DNS server. The name of the server might not be known to a server. The server might be down. The server might not be responding, so on and so forth. And also the server might respond with a text rather than a number, even though we expected it, because it's all text-based. And the worst of it all, the server might accept your connection and then do nothing, which is probably the worst failure scenario you can imagine, because it seems like the server is working, but it just does never give you any response. So this is an entirely different story. From the client perspective, you are still calling a single Java interface. So you think your job is done because you split your application, and rather than calling a standard Java class, which has an interface behind it, you are calling like something that automagically makes an HTTP request and unmarshals the HTTP response. But this is totally different. And we came up with all sorts of tools that are trying to fix it. So first of all, Hystrix, I really love it, which tries to shield you from external dependencies. If an external dependency like the triple interface fails, then it's going to be cut off and it's going to fail immediately rather than slowing down your whole system. Because as I said, the worst failure scenario you can think of is the system that does not respond, or responds with an error, but after many, many seconds. And if you're not protecting yourself from it, your system will become slow as well. And then the failure propagates over all these layers. So that's really bad. Then we came up with other tools like Zipkin, yet another fantastic tool which allows you to track latencies in your distributed system. So basically, you put a bunch of HTTP headers on top of your system, on top of your requests, and then this Zipkin tool, which is actually quite complex as well, tries to sample and track the delays, the latencies across your distributed system. It's like a profiler, but working on top of many components, many distributed components. And one more thing, I really like this quote, so I put it here. It says that internet is running in debug mode because pretty much all the protocols that we use publicly are based either on JSON or on XML. HTTP 1 was text-based, in contrary to HTTP 2, the protocol itself, not the bodies. And having everything encoded as a human-friendly strings means, first of all, that we are wasting a lot of bandwidth, and also that there are many, many reasons for the actual failure. Because there might be a problem with encoding, there might be a problem with malformed input, output, and so on and so forth. So what can we do about it, rather than just bragging that it's so bad? So what I'm proposing, and what I would like to share with you today, is something which is called a Hollywood principle, but at the architectural level. So how many of you know what a Hollywood principle is from programming? Anyone? Yeah, so I see a few hands. We don't have a mic, but I'm just going to tell it to all of you. So it's basically the quote behind the Hollywood principle is, don't call me, I'll call you. And it was coined when dependency injection frameworks and containers were introduced. And the idea is that rather than asking for dependencies, rather than asking the system, give me the class that I need, this relationship is inversed. So it's the system, it's the container that gives you the data eagerly, gives you your components that you need, gives you your dependencies, so that when you are about to serve your request, dependencies are already there. So like in Spring, you create a component and it has all its dependencies as a constructor arguments. That's a simple thing. Actually, the whole dependency injection is very, very, very simple concept. It's just passing dependencies through constructor. That's it. And all these frameworks and all these books talking about it, they're just trying to explain this very simple concept. But what does it mean at the architecture level? How can you make a Hollywood principle at the architecture level? And I'm talking about the data. So let's think about a really simple system that pretends to be a stock market. So when I'm doing, on the left side, I'm starting a request to a component called bidding. And this request, in order to actually figure out what to do, has to make a bunch of requests to a component called prices, to a component called portfolio. It has to know what the current price is. It has to know what's my current portfolio, so what kind of stocks do I have. And it has to somehow calculate the risk. And in the very end, it makes a request to a stock market to actually buy some stocks. This is totally not how these systems work, for several reasons. So the biggest reason here is that it's really slow. And by slow, I mean you have to make a request to one component, get it back. You have to make a request to another component, get it back. All the time you're paying the price of this network latency. You can technically parallelize some of this, so we can make several requests at the same time and then collect them using various frameworks. But still, it means that you have to pay the price of this network latency several times. And even worse, if one of these components doesn't work, your whole system doesn't work. You cannot make any transaction if you don't know the price, if you don't know the portfolio, if you don't know the risk, period. That's it. And that's how most of these systems are designed. You have fancy tools like circuit breakers with fallback. And you have these nice examples that in Netflix, when the recommendation engine doesn't work, they are falling back into bestsellers, which are easily accessible. But this is very rarely the case in our system. If we don't know what's the price of the stock, we cannot make a transaction. We cannot do a fallback to $100 because that's what we think the current price is for some reason. We have to have everything in place. So here we have this system, and the change I'm proposing here is to publish changes rather than ask for the data. So from the architect's perspective, from the PowerPoint architect's perspective, it's just a matter of inverting the arrows. So look closely. Previously, all the arrows were pointed into the right direction, because we were constantly asking something and then getting response back, asking something and then getting a response back. But what if I told you you could invert this relationship and say the prices component doesn't have a RESTful interface. All it has is a way of publishing changes. So it publishes the fact that the price of IBM stock has changed and it's now $170 something. What if the portfolio component, and this is even a more interesting example, what if the portfolio component was simply saying, okay, I noticed that you just bought some stock. I noticed that you just sold some stock. And that's it. It has no interface. The only way to figure out what's the current price and what's the current portfolio is to listen for these changes. And these changes, more often than not, are just deltas, which means that in order to figure out what's the current state, you have to listen through the whole history. So now what happens? Why are we doing this? The bidding component somehow subscribes to prices and portfolio. The actual framework and the actual protocol is not important. It can be WebSocket, it can be a queue, whatever. The point is, when it subscribes to this data, it can actually eagerly store this data on its own side. So the bidding component, the one on the left, can have its own internal, very optimized database that is very well suited to its own use case. For example, bidding component has to know what the current price is, right? That's part of its normal working. So rather than asking prices component, it can ask itself because it already has the data. And it has this data in the most optimized way it can. What's the most optimized database we can think of? A concurrent hash map, an in-memory store. And asking a concurrent hash map is way faster, way cheaper, and way safer than asking a RESTful interface in a second component. And the same applies to the portfolio component. Rather than asking what's the current state, what kind of stocks do I have at the moment, I can simply collect this data over time. And at some point, when someone asks me to make a request, when someone asks me to do some transaction, I have everything on my local site. So there's absolutely no interaction with the actual system. This does not apply, however, to risk component because it's basically a computation thing. So the risk component you have to ask the risk component with some specific set of parameters. It's really hard to think about this component, which is basically a stateless calculator. It's very hard to think about it in terms of publishing changes. So here I'm warning you a little bit. It's not a universal architecture. It's just something that you can consider. All right, so here we have this architecture. But there's yet another problem, and the problem is called temporal coupling, the worst of them all. So the problem with temporal coupling is that in order for two systems to work, they have to live at the same time. They have to be up and running at the same time. This means that when one system is restarted, or when one system goes for maintenance, it has a garbage collection, whatever, other system can't work. So effectively, they are synchronized. Both of them can't work. And the worst thing that can happen is that this thing propagates into whole your system. So a single longer garbage collection or a single restart causes a ripple effect across your whole infrastructure. That's a bad thing. So rather than, in a way, synchronously subscribing to events of every single component, what if we put another level of abstraction, because that's always a good idea. What if we put some sort of a database, like a big queue that's going to store all these events? So rather than subscribing to an event directly at the source, at the publisher, so rather than having this strong connection between subscriber and publisher, what I'm doing is that I'm publishing events into some centralized store, which can very easily be clustered. It can be a message broker, it can be a database. Notice that it has an append-only semantics, so it's an easy win, it's an easy implementation. So we need some sort of a database that's going to receive all these events. Pretty much everything that happened in your system, every single event, someone purchased something, a price was changed, a weather got different, whatever. Everything is stored into this one huge queue, which is basically a transaction log of everything that ever happened in your system. This is your source of truth. This is your full audit data. So here we have this database, and then we can subscribe to it asynchronously. And with this architecture, two systems that are inherently coupled with each other, the bidding component and the prices component, don't even have to be up and running at the same time. One component can be up for 12 hours, another component can be up for another 12 hours, and the system still keeps running. So that's a huge win. What else? Remember at the previous architecture, we were asking about the the portfolio at a given date. So we needed a data at effective date. This is a fairly common usage scenario in our systems. What we really want is we need a state of the world, for example, our portfolio, a couple of days back, because we need to retroactively do something. And this is fairly complex with normal systems because you somehow have to manually map your history, map your past history. When you're storing all the events rather than just a snapshot, rather than just a current state, it becomes much easier. Now, imagine you need to have a data at, 25th of January 2017. What do? Just as usual, you start subscribing to all the events from the portfolio component. You start to recreate the state. So you're starting with an empty portfolio, and then you just keep receiving someone bought something, someone sold something, bought, sold. You keep replaying these events from the very first one to the very last one to the present. And that's how you get the current state. But what if you need a state at 25th of January 2017? Well, when you reach the very last event on 25th of January 2017, the state you have currently after replaying all these events on the client side is your portfolio at a specific date. You don't need to do anything else. You just stop the loop in your code a little bit earlier. And that's it. So that's a very huge win. But doing this type of architecture is not only about advantages, there are always disadvantages. So there are a couple of them. So the biggest one is the fact that everything is eventually consistent. So this is an example of a Trello board. If you don't know Trello, there are many different tools like that. So there is Google Docs, there is Endomondo, there is various things for storing your notes, many applications that are supposed to work even if you're offline. And when you're offline, this application not only is supposed to serve your data, but it should also somehow support modifying the data. So what happens when I'm using Trello, for example, and when I'm using Google Docs or whatever, on my mobile phone and I'm disconnected, a poorly written mobile application will just tell me that it doesn't have internet connection and it has no idea what my data is. A little bit better, an application that is written a little bit better will keep a cache of the data, so at least I have a read-only access. But I still cannot modify anything. But if you apply the principles of event sourcing, but because this is what we are aiming at, so storing the events, what you can do is that when you're offline, but even when you're online, because this is consistent, rather than just mutating your state, so rather than just moving some internal data structure and when every time I'm modifying something on my Trello board, what I do is that I keep changes, I keep deltas, I keep modifying the data as a series of modifications. And when the application goes back online, when this mobile application goes back online, it just pushes all these events that it had in its internal queue, it pushes this into some internal server, and also it gets all the events that happened in the meantime on different devices or in the web browser. Does this remind you of something, that you are working offline, pushing changes, pulling changes? Nothing rings a bell? Exactly, Git. Git works exactly this way. It's an immutable log of changes. You don't just store a snapshot. You do have an append-only log of everything that has ever changed in your system. So that's a proven technology. But I started with disadvantages or caveats. So there are quite a few. First of all, eventual consistency, something we just keep hearing all the time with NoSQL databases. So when you're publishing the events, rather than just asking the system constantly, you will run into a situation that you don't have fresh data because one of the components was down, or maybe you have a huge backlog of data that you didn't manage to process on time. And people who are fans of event sourcing are claiming that this is just how the real world works. When you're, for example, booking tickets in an airline, not everything has a central database, and it might happen that the same ticket was sold twice to two different people, something which we painfully were reminded of quite a few times in the past. So this is an inherent property of the real world, that we don't have a central database of everything, and the real world is eventually consistent. But we got spoiled by relational databases, which pretend to have everything always in sync. So we have to think about eventual consistency. This is going to be a huge pain if you don't think about it in advance, if you don't think about the fact that you might have stale data. It can be milliseconds, or it can possibly be even hours, and you have to react accordingly. Another caveat is that it costs to rebuild your, it's called projection, so this local copy, this local optimized database. If you're subscribing to your portfolio and your portfolio was built for several years, it will actually take several seconds, maybe minutes, maybe even more, to get into the current state of affairs. And there are ways to overcome this. You might have some sort of, it's called snapshots, which is basically having the current state taken every 100 events or every week or whatever, so that you no longer always start from the very beginning. But it's yet another thing you have to think about, and it will make your life harder. On the other hand, when you have this audit data, you can actually take these events and replay them even on your local developer machine, which means that if there was a bug 1 month ago, and you no longer have logs, you have no idea how the database was looking 1 month ago, you can still check in code from 1 month in the past. You can take the events from production, you can replay them on your local machine, and at least you have a full control over how the production was looking 1 month ago. So it's like a debugger that works in any past point in time. So that's a cool thing. And one last thing is, or actually I'm going to leave you with this philosophical question. Do you think World Wide Web, websites, can actually work this way? Could World Wide Web use this type of architecture? And why not? Which also means this type of architecture is not a good fit for every single problem. And I would really be afraid, and that would be really disappointing if you leave this presentation and suddenly try to rewrite everything. It's just an alternative way of building your systems. That being said, I would like to thank you. Thank you very much.